Okay, welcome back, everyone. When we try to invert, or when we try and do inversion for a model or a problem which has more than one kind of parameter, so we are trying to invert for multiple parameter classes, then trying to understand the sensitivity of the algorithm to different or to each of these parameter classes attains a lot of importance. So sensitivity analysis of for a model parameterizing in terms of different classes of parameters has been performed by different authors, and one of them, Tariq, is here in the audience. So I'm going to speak about one such method. Just before the break, at the end of the talk, we heard some speakers. We heard John Anderson talk about the null space, and so it's all related, it's all interweaved. So I'm going to talk about the inherent trade-offs that we just saw in the previous talk in terms of something called radiation pattern. Now, radiation pattern is not what you might think of in the conventional sense. So we think of a source, and then the source goes off, and then there's energy radiated in a certain manner around the source. So that's not exactly what we're looking at. What we're trying to understand is when energy is incident on an anomaly in one of the model parameters, then how is this energy scattered around the anomaly? And the way it's scattered as a function of angle, for instance, will tell us quite a bit about which of those model parameters can be resolved for a given configuration, and gives us hints about how we can proceed in the inversion or in the inverse problem. So in this case, again, we'll be restricted to using the 4 model parameters that I showed in the previous talk, and we'll also look at just transmission experiments. But the derivation that we have in this presentation is quite general. It can be used for reflection data and can be extended to any model parameterization. So I'm going to very briefly describe how we obtain the expressions for these radiation patterns. The details, of course, are in the appendix at the end of the report. I'm just going to give you a very brief overview of the derivation. So we start off with the elastic wave equation, and we're looking at a perturbation in the model. So we've got a source at xs, a receiver at xr, and there's a perturbation at a point in the subsurface x dash. So now we want to express the elastic wave equation in the Born approximation. So we've got the Cijs. We perturb the Cijs by delta Cijkl, which results in a perturbation in the wave field. And then we express, so we have a wave equation, an elastic wave equation in the perturbed wave field, and it's expressed in terms of a source function which has the perturbation in the stiffness coefficients embedded in it. So one of the ways of obtaining a solution to this wave equation is by writing it in terms of Green's functions. So we've got the perturbed wave field at the receiver location xr as a function of frequency, so we go into the frequency domain, and it's given by an integral which contains 4 terms. We've got the source density function at the source location xs. We've got the perturbation in the stiffness at x dash, and then we've got the spatial derivatives of 2 Green's functions, one of them between the source location and the scatterer, and then the other one between the scatterer and the receiver location. And you might recall that this particular expression contains these two, the spatial derivatives of the Green's function might remind you of the gradient expression we had for the FWI in the previous example. So there we had the spatial derivatives of the forward and adjoint wave fields, and here we have the spatial derivatives of the 2 Green's functions. So, and that's because you're looking at the Frechet kernel in both cases. Right, from here on, what we do is we substitute the Green's function by the asymptotic Green's function. So now you got this huge expression, but I'll walk you through the entire thing. So the perturbed wave field at xr is an integral which contains fm, which is the source density function at the source location. Then there's a term a, which is a function of the frequency, the group velocity, the phase velocity, and the distance traveled along the ray path. So now we are, since it's the asymptotic Green's function, we're thinking of rays, we're thinking of modes. So we've got the p wave field and the s wave field, on which will depend the group velocity and the phase velocity. And then we've got rho, the density, and k is a parameter that depends on the the curvature of the slowness surface. Then you've got these p's, which are the components of the unit slowness vector. S and R denote source and receiver sides, respectively. Then you've got the g's, which are the components of the unit polarization vector. And S and R are the source and receiver sides again. Delta Cijkl is the perturbation in the stiffness at a point in the subsurface. So from this entire expression, we isolate the radiation pattern. And for a model parameterized in terms of Cijkl, it's this expression here. So again, omega is the radiation pattern. We've got the components of the unit slowness vector, P, and the components of the unit polarization vector, G. S and R denote the source and receiver side, respectively. So far, we have not made any assumption about the background medium. It's anisotropic, arbitrarily heterogeneous. And from here on, we can use again the chain rule to parameterize the model in terms of any set of parameters that we fancy. So could be the vertical p and s wave velocities and epsilon and delta, or we could be looking at the vertical p and s wave velocities and the p wave, NMO, and horizontal velocities. We could have express the model in terms of eta, whatever we want. So we use the chain rule, and so in this study we're just looking at the second model parameterization. And at this point, what we do is, just to make things simple, to get a closed form expression which is very simple and intuitive and gives us a very good understanding of what's going on, we make an assumption about the background medium. And the assumption is it's homogeneous and isotropic. Now the tests we performed, or the tests I showed you in the previous presentation, did not have a background that was isotropic. It was VTI. And here we assume that the background is isotropic. But I believe that it's not going to make a huge difference, because all we want to do is get a qualitative understanding of what the radiation patterns look like and how they're going to affect the results of FWI. Right, so I'm going to show you the radiation patterns for P waves and S waves for a model that has been parameterized in terms of the four velocities. So what this tells us is we've got an anomaly in VP0. Suppose you have a model with an anomaly in VP0 at the center at the origin, and if there's energy incident on it, it's going to scatter the incident energy in this manner. Now again, this is specifically for the case of transmissions. The incident and the scattered thetas, the angles, are equal in this case. But this is derived from the previous expression, so we could go on from there to transmission or reflection, anything we want. So here we've got the maximum energy transmitted along the vertical symmetry axis, and then the energy decreases on either side. And this might be sort of intuitive, because we expect the vertical p wave velocity to scatter incident p waves mostly in the vertical direction. In the case of an anomaly in VNMO, we see that the energy is scattered such that the maximum is at 45 degrees, and the maximum value is 1/4 of that for the vertical p wave velocity. So this suggests that when we do the inversion, this might be a parameter that's less, to which the algorithm is less sensitive to. And this is counterintuitive, because when we do conventional processing, VNMO is generally the parameter that's quite well constrained. Now if you look at an anomaly in V horizontal, you see that most of the energy is transmitted along the horizontal, along the symmetry plane, and then it decreases on either side of the symmetry plane. And this again might be an intuitive result. But if you look at the expressions, they're not just simple. It's like in this case, it's sine to the 4th power. So it's not even for the simple model. The expressions are not sort of something you would just imagine. They are much more involved. So now we go on to S waves, and I'd like to mention that you might have seen this, that for this parameterization, an anomaly in VS0 doesn't scatter or doesn't scatter the P waves. And similarly, in the case of S waves, when S wave energy is incident on an anomaly in VP0, there's no energy scattered for this particular parameterization. It might change when we change the parameterization. So again, we have an anomaly in VS0, and you see that energy is scattered equally in all directions. The radiation patterns for VNMO and V horizontal are exactly the same for shear waves. Now let's try to use these radiation patterns and understand the results that we got for the transmission experiments. So here is exactly the same experiment that I showed you in the previous presentation, the first experiment that we had, an anomaly in epsilon. So we want the inversion algorithm to update epsilon by 0.04. So in this case, a change in epsilon results in a change in V horizontal. So among the 4 parameters we have, the 4 model parameters, V horizontal is the only one that needs to be updated. So we'll just look at the radiation patterns for an anomaly in V horizontal. These red arrows indicate the aperture for the given source receiver geometry. And we can see from this diagram that most of the energy that's scattered by the anomaly in V horizontal, most of the P wave energy is recorded by the receivers. That's what the aperture tells us. So we would expect the inversion algorithm to update the V horizontal really well. And the S waves are scattered. Most of the scattered S wave energy is also recorded by the receivers for this configuration. And that's what we see here. So because of the fact that V horizontal is updated by the inversion algorithm, we see an update in epsilon. None of the other parameters are updated, and we got a good result. Now we go to the anomaly in VP0. So we want an update in VP0 by 9%. So here again, an anomaly in VP0 results in anomalies in NMO and V horizontal. So we want the inversion algorithm to update all 3 parameters, and it would depend on the radiation patterns for all 3 parameters. So let's look at the radiation patterns for these parameters. Here you see that in the given aperture shown by the red arrows, a very small portion of the P wave energy incident on the anomaly in VP0 is recorded by the receivers. So this means that the update in VP0 wouldn't be very significant, or at least as significant as we want it to be. So here it seems that a lot of the energy scattered by VNMO are recorded by the receivers, but the problem is that the amount of energy scattered itself is very small. So again, this might lead to a problem in updating VNMO. Here it seems that most of the PO energy scattered by the anomaly in V horizontal will be recorded by the receivers in the aperture. So we would expect a very big update, or the inversion algorithm to do a good job of updating V horizontal. And here we look at S waves. So again, VNMO and V horizontal have similar patterns. So we expect the S wave energy to be scattered similarly by both VNMO and V horizontal. But out of all these radiation patterns, I think you can agree that V horizontal is the one anomaly that seems to that you'd think the inversion algorithm would do a really good job of updating compared to the rest. And what would that mean? If V horizontal is the only one that's updated, or updated more than everything else, then you'd have an anomalous update in epsilon, a wrong update in epsilon. And that's what we see here. So we wanted an update in VP0. There is an update, but it's much smaller. And there's a wrong update in epsilon. So which suggests that if we based on the results here and based on the radiation patterns, if you want to perform FWI for this source receiver configuration, we should be trying to update only V horizontal and none of the other parameters. Even if there's an anomaly in VP0 as we see here, we should not try to update VP0 for this source receiver configuration. Right, now we look at an anomaly in VP0 where the sources and receivers are horizontal arrays. So let's look at the radiation patterns for this configuration. The red arrows indicate that most of the scattered, the P wave energy scattered by VP0 will be recorded by the receivers. So here we expect a really good update in VP0. The update in VNMO, we expect it to be tiny. And worst of all is the update in V horizontal. So here you see that in the previous case, whereas V horizontal was updated really well, here we do not expect a significant update in V horizontal. And these are the patterns for the S waves, again VNMO and V horizontal. So both of these have been plotted separately. So the P waves have been plotted normalized separately as opposed to S waves. So the relative contributions are still something we're not quite sure how they work. But the fact is that the presence of S waves do seem to provide some constraints, but we still need to figure out the relative effect of the constraints. So again, I think you'd agree with me that VP0 is the parameter that seems that in this case would get updated the most. And if that happens, and if V horizontal and VNMO do not get updated well, to the extent that they should, then you'd have faulty updates in epsilon and delta. And that's exactly what we see. So we see that the updates in VP0 are really good, but we have faulty updates in epsilon and delta. So for this source receiver configuration, based on the results and based on the radiation patterns, we should not try and update anything other than VP0. And finally, we go on to an anomaly in VS0. So if you remember, an anomaly in VS0 scatters the P wave energy equally in all directions. It was a circle, which means that the experiment should, no matter how the sources and receivers are configured, whether they are horizontal arrays or vertical arrays, they should still give us pretty much the same result. And that's exactly what we saw. So here, I do not have the results for both the source receiver configurations, but we see that we want the update to be close to 19%, and it goes to 16%, which is close enough for the given aperture we have. So the purpose of this study was to understand or to get an analytic description of the model parameters, the sensitivity of the model parameters to FWI. And we do this by obtaining radiation patterns for the model parameters, the 4 velocities. So in this case, we just obtained simple expressions for isotropic backgrounds. Again, the goal was to get a qualitative understanding of the radiation patterns. And we see that VS0 and epsilon are constrained in the cross-hole geometry. I'd like to thank lots of discussions I had with Andreas and Tariq. Thank you very much.